Welcome back. In our next set of lectures, we're going to be looking at statistical tests that we use for nominal types of data. We're going to refer back to our decision tree diagram here, and on the right-hand side, we're going to be looking at nominal types of data, and we're going to start with the chi-square test. And this is where we would have greater than two groups of unpaired data. We can also use a chi-square if we have two groups of data, so it can be used in either case. The key is that the data does have to be unpaired. Our objective is to appraise if a chi-square statistical test was appropriate for analyzing data provided in a scientific journal. And so chi-square is used to answer questions about rates, proportions, or frequency, so our nominal types of data. There are two types of chi-square analysis. There is the chi-square test of independence and a chi-square goodness of fit. And we will be focusing on the chi-square test of independence. And this is also known as the chi-square test of association. And this is commonly used in biomedical statistics and can be used for comparison of two or more groups, as mentioned before. The chi-square goodness of fit test is used usually to compare sample groups with data from a known population, and so it permits researchers to assess whether the sample group is drawn from the same population as the standard of comparison. And so we can see this, for example, in like some genetics type studies. But for the purpose of this course, we are going to focus on the chi-square test of independence. So some of the assumptions of chi-square that only frequency data must be analyzed. And so this data can be derived from data that are ordinal, interval, or ratio and transformed into nominal frequency data. The events must be independent within a sampling group or unpaired. And no cell of a 2x2 matrix or a 2x2 table or less than 20% of the cells of a larger matrices, so larger tables, may have an expected frequency of less than 5. And we'll get into that a little bit later, what an expected frequency means and what it means that this can't be less than 5. If this were the case, we would be using another statistical test known as the Fisher's exact, which will be in the next lecture. There must be a logical or empirical basis for classifying data into nominal group. We're not just transforming this data into frequency data so we can use a chi-square. There must be a logical or empirical basis for doing this. The sum of all the expected frequencies of all the cells must equal the sum of the actual observed frequencies for all cells. And this will make a little bit more sense when we look at the formula for a chi-square test statistic. And the sum of all the observed frequencies minus the sum of all expected frequencies must equal 0. There are some limitations of the chi-square test. It can't be used for paired or related samples, as we saw in our decision tree diagram there. And it doesn't indicate the strength of an association. It merely indicates that there is an association that exists. So for example, if we have a p-value that ends up being less than 0.001, it doesn't indicate a stronger association than a p-value of less than 0.05. So, for example, you are a clinical pharmacist working in an outpatient pain clinic, and you're interested in assessing, based on gender, the distribution of patients you have that are on pain medication A versus pain medication B versus pain medication C. And we have our matrix here, or our table, so it's divided by males or females, and we look at each of the three medications, so how many of each patient are on each medications. The values at the bottom here and on the side are just the totals of the row and the respective columns, with the total of all the patients here on the lower right hand corner. So we have 267 patients total. So like always, we want to go through our methodology here. So we want to make sure no assumptions are violated. I'm not going to restate all those assumptions, but you can refer back to the 6 assumptions of the chi-square. We want to state the null and alternative hypotheses. So our null hypothesis would be that there is no association between patient gender and pain medication use. Our alternative hypothesis would be that there is an association between patient gender and medication use. We want to state our alpha, which is 0.05. Next, we want to calculate our degrees of freedom. So our degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. So in this case, we have 2 rows, one for male and one for female. So it would be 2 minus 1, which is equal to 1. We have 3 columns, one for each pain medication, so it would be 3 minus 1, which is equal to 2. So 1 times 2 is equal to 2. So we have 2 degrees of freedom. Next we want to find our critical chi-square value, and again we would use the chi-square table for this. And so we are using a significance level of 0.05 and a degrees of freedom of 2. Again we would have a chi-square value of 5.99. And so from our table, we saw, again, our chi-square value is 5.99. So if our calculated chi-square test statistic is greater than 5.99, we can reject the null hypothesis. And so how do we calculate a chi-square statistic? So we have a formula here at the bottom, which is equal to the sum of all the observed frequencies minus the expected frequency squared over the expected frequencies. And we're going to break this down a little bit more. So referring back to our example here, our expected frequencies is what we would calculate for each cell in our table here, or each cell of the matrix. This is equal to the row total times the column total divided by our grand total. Looking at our first cell here, we'll calculate an expected frequency. This is what we would expect to see in this column. However, this will differ from what we actually see, or our observed frequency. That's what we actually got out of the study. So our expected frequency is equal to 138, that's our row total up here, times our column total, which is bolded down here, so 176, divided by our grand total. So we had 267 patients in this study, so we would divide that by 267, and we get 91. So this would be our expected frequency that we've calculated for this particular cell. Our observed frequency, however, is 74. So next we're going to calculate the rest of our equation, which is right here, observed minus our expected squared divided by expected. So observed, again, for the first cell here would be 74 minus our expected 91, and all of this is squared, divided by the expected, which is 91. So we get a value of 3.2. This is specific to this cell. Again, our chi-square test statistic is equal to the sum of all of these observed minus expected squared divided by expected. So we would calculate this for each individual cell, which is what I have here in the brackets. So the second set of brackets here is what we would add up for each cell. So 3.2, which is from the first cell there, 0.2, which is from here, 8.5, which is from here, and so on and so forth. So we get a grand total of 24.6. This would be our chi-square test statistic. So since 24.6 is greater than 5.99, we can reject the null hypothesis and say that there is a significant association between gender and type of pain reliever used. There are also online software programs we can use. There's several different ones, and we'll use this one to show the online example. So this time we're going to go under frequency data, since we're dealing with nominal data here. And we're going to select, there's a couple different chi-square here, chi-square programs here. We're not going to pick the chi-square goodness of fit test, because that's a little bit different than what we want. We're going to do this one here. It's a chi-square, Kramer's V and Lambda, but we'll just be looking at the chi-square value. So this program allows us to select the number of rows. We know we have 2 rows, one for male, one for female, and we have 3 columns, one for each pain medication used. And so this will kind of gray out the rest of them here. And you can enter our data straight across how we have it in our table here. Okay, I've already pre-entered the data here in the same way that we have in our table, and we hit calculate, and we can see here that we have a chi-square value of 24.51, which is similar to the 24.6 that we calculated. It'll be a little bit off since we're doing it manually. Again, it calculates the degrees of freedom for us, which is 2. And we have a p-value of less than 0.001, which does indicate to us that it is significant since it's less than 0.05. So in the next set of lectures, we will be looking at the Fisher's exact test, which is somewhat similar to the chi-square, so stay tuned for that.